Hi guys, this is a continuation on my previous video about fixing the we're working on fixing the TCPA300 current probe amplifier. Last time I mentioned this IC appeared to be giving out a bad signal. That doesn't appear to be the case. This is a octal buffer with enable, and all the outputs seem to have that problem, but when I probed the power lines, especially plus 5 volt analog, that analog voltage is dropping, so something else is likely the problem. Something on this board somewhere is shorted. So I'll have to go start looking around. I notice on this other part of the circuit around here, there's a bunch of signals that are high for the same amount of time that pulse drops low, and you can see some of these look like they start out high and then drop down, so whatever this chip is driving may be causing the short. So let's continue looking. I'll see if I can figure out what this chip is driving. I'm thinking it might be these relays. It seems that this section of the circuit does indeed drive the relays, probably through some transistors or FETs under the relays as a buffer, but I'm not entirely sure that that voltage droop we saw on the 5 volts is actually a problem, because it seems to be trying to switch all the relays at once at that time. When you switch them all normally, turn it back on, see if I can get a view of one of them switching. Those seem to switch pretty normally. Let me reset it to the way the voltage scaling it was before. Yeah, it only switches, I think, 3 at once when you press either the coupling or range buttons, but it switches all 6 at once when you press the degauss button. And I also looked up when the probe starts flashing those 2 LEDs, that actually means an error code, and this four LEDs here indicate what the error code is, and this one, binary 2, means that there was a problem zeroing the DC offset. And when we're on the AC coupling range, the offset is off. It's quite a bit negative for some reason, so that might be what's causing the problem. And before they gave this to me, they sent it into a guide to have it repaired, or to see if it could be repaired. He said he found a resistor that was blown. I think it's this one right in the center there, and they replaced that. That didn't fix it, so they said they need to put a new board in it. At that point we said we'd just buy another one. It's not too much more expensive. So maybe they put the wrong resistor value in, or whatever surge blew that resistor blew something else after it, so I might have to take out this board and see what's going on there. Okay, I removed that blown resistor that was replaced by the TECs, and the left side of it, our R211, is connected to the output. The right side gets to about -8 volts when the probe is on. So I connected one end of the multimeter to that -8 volts. Put it on what is it? Continuity mode, continuity beeper, and then we can put one probe on there. And I don't know if I can hold the camera while doing this, but you sweep it across all the places you want to see where it's connected, and the fast continuity beeper will beep when you run it over it. Let's see if I can demonstrate this. Okay, let's see how probe cam works. I've already figured out where it goes, so I'll just go. It was on this chip. If you just sweep it across, and there we go. It finds where it is, but you can quickly sweep it across. If I connect it right on the other end, you can sweep it across chips quickly and figure out where it's actually connected. With a fast continuity beep, it'll you can sweep it very quickly and immediately find where it's connected. It's connected to a few around here. I think one of them is right near 0 ohms, so that's the one that's actually connected. I think that was this one right here. So this chip, if enough current flowed through that resistor to blow it, it's quite likely it blew this chip. Okay, I desoldered that chip now, and if we probe the node here, or actually this other one that was at -8 volts, it's now at 0 as we expect, and I believe that one went to, I think it was either here or there. Yeah, either here or there, and the one that's switched onto that is either this one, which is at 0 volts, or this one, which is at about 0.2 volts. And this other one we measured before, or here, that was at -8, is now at 0. So I'm thinking that blown chip, is causing the problem. So I'll have to order a replacement for this and see how it goes. Probably only a couple of bucks. I think it's worth the try to get this thing working. Okay, I ordered in some replacement analog switches. So let's just cleaned up the pads here, so let's put that in and see if that fixes it. Okay, the new chip's in, and we're ready to try this out. Let's turn it on. Okay, no smoke, that's a good thing. Let's just put the cover on the probe. It should be good enough, and then let's press degauss to see what it does. Oh, it seems to be working. It passed degauss. That's very good progress. Let's see. I borrowed a known good amplifier and a good probe from work somewhere. Yeah, this is a working probe, so I can test it with that and compare the outputs between the known good amplifier and this one. So let's hook up the working probe and give it a try. I also tested this probe out on the good amplifier, and the gain, the probe itself is the melted probe is damaged, and that's why the gain was wrong earlier. So I'll set that up and let's try making a measurement, see if it's accurate. Okay, new probe's connected up. Let's turn it on and see if this one calibrates properly. That one seems to be working. It's doing what it normally does on the scope. And the moment of truth, let's connect it up. And it does seem to work. What do we have for current here? 7.7 amps, and the RMS measurement is 7.6 amps, so it does seem to work properly. I think this thing is fixed. Probably have to check the high frequency response as well. I'll set up something with a signal generator and compare the output of this amplifier with the good one. Okay, we've got the signal generator. Just a short across the output with a probe clamped around that. I've got a faster scope because this is a 100 megahertz current probe, and a 100 megahertz scope is not good enough to test it. So this is all set up. I've got a wave coming out of it. I'll just take a couple of prints, probably one at this zoom, one zoomed all the way in, and compare, then switch to the known good amplifier and compare them. So let's do that. And the zoomed in one. And I'll just persist this so we can quickly check when I swap the probe over. And we can do that right now. Okay, new amplifier is on, and the waveform looks quite similar, except there's a little bit of offset, so I think that's normal at these very low volts or amps per division range. Just increase it, zoom it up, move it up. That looks pretty close. print that and zoom out. Now that does look different. There's no little oscillations there, so something's different between these still, though. I'll have to look into. Actually, come to think of it, I remember vaguely seeing a distortion like this before when I was using one of these probes, so it's not impossible that this is a quirk with this design or with this older probe, because if you look at the back, this good one is serial number B027225. This one is an older serial number, B021509. So it's possible that they've changed some component value or changed something about the circuit to correct this bug in the later versions. I'll have to compare this with the other amplifiers at work. Hopefully we have another one of this vintage, and if it displays the same symptom or same bug, then this amp seems to be working fully. I also noticed that when you set it to 10 amps per division and scale it up, the problem is a lot less pronounced. The oscillations die out a lot faster. Okay, I swapped the newer current probe amplifier I had before with an older one. This one is serial number B019760. It's older than this old one, the blown one. And this one, the older one, does also exhibit the oscillating problem. So it doesn't actually seem to be a problem, it just seems to be a bug in these older probes. So this broken one does appear to be fully functional. I thought I may as well go over the operation of the amplifier that I figured out while doing this debugging, which might aid someone else who's debugging an amplifier like this. Starting from the input from the probe itself, the first chip is a differential amplifier. That one is a switch, at least this channel, the channels on closest to pin 1, switches the output of this amplifier into the main hall amplifier that feeds the probe. I believe it also switches in the calibration signals coming from this chip, which is a multi-output DAC. There's some more analog switches, I'm not sure what they're for. The inputs to these two switches come from this buffer over here, which I believe is used to transfer the digital signals from the noisy digital domain to the clean analog domain. There's another one over here. I think this I believe is a shift register used to generate the relay drive signals, so you don't need to take up a large number of chips to drive them all. Those signals are buffered. I believe there'd be FETs or transistors underneath to actually drive the relays. These are latching relays, so they have a coil that requires positive and negative. This amplifier, this is a 180 megahertz power amplifier, and that seems to be used only for AC coupling. When it's in DC coupling, this gets no signal. When it's in AC coupling, this gets the signal. These pots control the gain of the different attenuator stages, and depending on what range you have it set, some of these resistors are used as termination resistors, or as trims for the termination resistors. High frequency adjustments need to be done by these fixed inductors. I guess they affect the high frequency response, and the engineers at Tech have added them to get good high frequency response. This cap is the AC coupling cap, which is switched in when you put in AC coupling mode. Yeah, as far as I can tell, other than this, which is only used in AC coupling, the signal coming out of the transformer goes straight through the attenuators, optionally not attenuated at all in the 1 amp per volt range, straight into the output BNC. If you look up the manual on this, there's a decent amount of info on these adjustments and how to calibrate them. It gives you the full procedure. I also noticed when the probe is off, these relays are in positions such that the signal from the Hall sensor transformer, or the sensor transformer output, can go straight through without any attenuators or termination to the BNC. And it seems that if you apply a high voltage to it, it'll blow those two 10K resistors and this chip. And it doesn't seem to damage anything else. While I have this probe out, why don't we take a look at how things have changed in these amplifiers since the late 70s, when this AM503B or AM503 was made. So let's pull this out of the power supply. Get it. There we go. Quite a bit bigger. Just pull the top cover off. Now there's some classic electronics in there. Classic Tektronix custom chips. Old school RF design with all the resistors soldered together. Yes, this is factory, this hasn't been modified. The wires running all over the place. Contrast to the new one, all in one board, no wires running all over the place. Let's see what's on this. Let's flip this one over to the other side. I think this is a 4-layer board. I remember seeing, yeah, there's the layer indicators, which is quite advanced for that time. That was expensive. Just see if we can trace out the signal from this, how the signal flows through this one. These old probes work in exactly the same way as the new ones. I believe the signal from the probe that comes down these wires into this socket, then comes through here. There's these little attenuators, thin film laser trimmed attenuators. Let's see if I can open one of these up and show you. Yeah, these things have tiny, focus, tiny little resistors on them. This one's just a termination. They also make attenuators. You can see the little lasers remove part of the resistor to trim the value. This one acts as a termination resistor. Just put that back on. And there's a bunch more of them under here. This thing is the range selector switch, which as you turn the knob, moves these little contacts up and down, switching in and out these attenuators. And that's one thing I don't like about the design of this particular amplifier, is the full strength signal comes in, and when you turn the up to the high ranges of amps per division, it just attenuates the signal all the way down, and then after it's been attenuated, it amplifies it back up again through this part of the circuit, then goes out. That makes it quite susceptible to noise. Back on the other side, they've added these little brushes that connect the knob to ground, because whenever I put my hand near the knob, noise would get injected in and amplified. And the original probe actually has one of these brushes. I added some more to get better contact. The PCB on this one was all drawn out and laid out by hand with all the beautiful flowing curves. You don't see that on modern PCBs. Here's the Hall sensor connection coming in from the probe. It goes through from some various amplifiers and over to the discrete power amplifier, equivalent to this one on the new probe. And I believe this is one side of the transformer that goes out to the probe, and the other side comes back, as I said earlier, and then goes into the attenuator. And there's some amplifiers, more amplifiers here after it comes out of the attenuator. Tektronix custom chips, I think those do amplification and some frequency correction. There's a bunch of pots that are used to adjust the response. Use a procedure in the service manual to go through and adjust all the you look at the waveform and adjust these pots to get the best square response. Another thing you might notice is there is no custom parts at all in this TCPA300. There are a couple of custom parts in the old version because they needed custom parts to get the high performance required, whereas now you can do the whole thing using only off-the-shelf parts. Here's a date on this current probe, made in copyright 1979. So, looks like I'm going to have to be on the lookout to buy a probe to actually make use of this amplifier. Anyway, I hope you found this video on these current probes interesting. Thanks for watching.